Okay, for record, all the students are here. So just now we look at a few factors that can influence the drag coefficient. So shape, Reynolds number, compressibility, surface roughness, front number, and body drag. So we look at a few charts later on. So on the chart below question 25, this chart is for shape dependence factor.
Sure.
Yeah.
Yes, now for the friction drag too.
Which one?
For the friction drag.
This one, is it? Or before this, is it?
Before that,
Yeah.
we got the coefficient of drag friction, right?
Yeah.
The equation for that is fixed or it's only for that diagram?
Which one? This one, is it?
No,
Or
the other song. That one.
this one, is it? No, this one is the question. This one from the question. Or the one that in the question 20. Question 20. This one, is it? This one. Is it
No,
this
sir.
one?
It's question 23.
Okay. Yeah, what is your
I,
what
I,
area? Don't understand.
I mean the coefficient that drag friction. I mean the equation for the.
Oh, okay.
It is the fix
Uh,
or it's only for the that diagram or that question.
Only for this setup only.
Mm.
For in general is this equation. In general is this one. But this one for plate you have the B. So cylindrical, the equation is this one. This one fixed. This drag is in general, and then if you focus on friction drag, then we don't have the pressure component. We only have the shear stress component. This one, by definition, is like this. Okay, and then the rest is just a modification from the statement from the question itself. This is the fix already. CD equal to D divided by half rho U square A. We modified to the coefficient that we need. So if you're looking for friction, then your drag on the top here become friction drag. If you don't write the friction, means it's a general drag. Okay, and when it comes to pressure, so you see the pressure drag also same. Only you see now the pressure drag, the drag on the top of the equation now become dP, become pressure, and then the coefficient become dP, become the drag for the pressure drag. Right? And then the rest, you need to look back the component. For example, pressure drag linked to pressure. So the general equation that you have pressure and the shear stress, you only look at the pressure component. Okay. Yeah, any more question? Do I answer your question?
Yeah, okay. Sir.
Yeah, okay. Now we look at the diagram for the shape dependent. So the first diagram under question 25, on the left hand side is CD. So this one is a general, if you do not see any small number beside the CD here, it means it's a general drag value. So general drag coefficient versus the ratio of the length, and the D length is given in the diagram. So length is from the front to the back, the length here, and the D is from the top to bottom, the distance between the top and bottom. So the ratio is given like this. So if you have all this number, what does it mean? If you have 1, means that your L and D is the same, meaning that you have a circle, a full circle body. If you have L over D is 1, it means L equal to D means you get a round circle at this line. Okay, Now, what happens if we have we have 6? You have 6, it means if your D is 1, if your D is 1, how you get 6 means your above is 6. If you fix your D and you increase your L, you'll get 6. So it means at this 6 number, D, it means the length is 6 times of the diameter. So it's at this here, if you draw out, you illustrate the ratio below here, it means this is a round circle. Apologize for my drawing. And this one is a little bit like this one. So this is D, this is your L. Your L is 6 times of your D. So you become like this. So the shape, as you increase the ratio of L over D, means you change the shape of the object from round circle to a airfoil shape like that. All right. So what happened to your drag coefficient in general? So CD given by D divided by dynamic pressure, half rho U square, B times D. Again, what is B times D? It means that what seen, the BD here, is area. This is area. So area seen by the upstream velocity. It's like you shine a torchlight, the area that you see when it touch. So when it touch the area, this is the area that you see. If you view from the front, you are seeing this one and times the length here. So you're seeing this length, D, times the L, or times the B length, width. So you get the area here, this one, okay? So if you increase or you change the shape from circle to an ellipse shape, like that, so what happened to your drag? So you can see, so the line, solid line, if your flat plate solid line, it give you an arrow. This arrow refer to flat plate. We have flat plate. Your drag coefficient, that means will decrease if you have an ellipse. For example, plate. Why you use a flat plate? But anyway, in general, you'll see that if you improve your shape, become from circle to ellipse, the drag coefficient will reduce in general. Okay, your CD will drop. Okay, your CD will drop. And this dotted line is also, wait, this one. No, I think this solid line refer to this one. This one B and L. Okay, this equation refer to BL. This line refer to BD. Okay, solid line refer to B and D. Dotted line refer to B and L. Okay, B is the width of the object. Okay, so this graph gives you the general idea. What happens if you change the shape? It will drop. It will drop. So this graph, CD here, it will tell you that it is a combination of friction and pressure drag. If you do not see anything below CD, if you see F means friction drag. If you see CDP means it refers to the pressure drag. Okay, F refers to friction. If you see a CDP means it refers to pressure drag. Okay, then shape, again, if you look at the diagram below 25 on the right hand side, you'll see this diagram. So you'll see that if you change shape from square to a rounded front area to a rounded front area and ellipse teardrop shape at the end, the CD will also dropping. So from 2 drop to 1.1. If you have a round front, drop to 0.5. So this process, a technical name from this shape to this shape, we call it streamlining. Okay, streamlining. If you go to work in the surface, to work as a design engineer, so if you want to modify object geometry, reference to the upstream velocity, the process is called streamlining. So this word also important for your assignment number 1, for your info. Yeah. So for turbo machine, yes, of course, a little bit about streamlining, but not much. But streamlining will help you in your assignment 1. Okay. Diagram above question 26. As you can see, there are 2 different shapes here. So we assume in these 2 cases, although we have a different size of this one, but the drag, the total drag on object 1 on the left will be same as total drag in object number 2. Okay, so drag in object number 1 will same as drag number 2 by their own setting. Okay, so this is just a pop quiz question. So one of it is ask you, what do you think if you're streamlining the shape? What will it affect the drag? So from here, it gives you some illustration. If you're streamlining the shape from a square, sharp corners to a ellipse shape, or teardrops or airfoil shape, then you'll see the CD drop. CD drop, you substitute this value to drag equation. Of course, the drag will drop. Yeah, different size, same drag means that if you have the same drag, so for example, drag A, drag B, so your drag A same like drag B. What is the equation for drag? Half rho U square CDA equal half rho U square CDA also. But for the first case, we have CDA case, area of A case, and then CDAB case and AB case. So if the scenario is set that the drag between these 2 bodies is the same, the only things, because this one will be the same, the front half rho U square component will be the same for both sides. These are the dynamic pressure, both in the same medium, which means in the same air or water. So rho will be the same. What you can play with is the CD and the area that the upstream velocity contact with. So if you want to have the same, these 2 CDA on the left, you must balance with the CDB on the right. Okay, so it's logic. If you, for the case 1, you have the CD value higher than the CD value for the right hand side diagram, because these two value must same. So it's always logic to have cylindrical cylinder on the left. The value of CD is higher than the CD on the left, on the right here. Okay, so this yeah.
Sir,
Yes.
it is the CD same when the shape is different.
You mean this one, CD?
Yeah.
Okay, so this is just explain what happened if we apply the drag equation. Yes, of course, when we change the shape, the CD will drop. But what happens if we have a two object, one is on the left, one on the right, and the drag is the same, means the total drag acting on these two bodies is the same. For example, we have 100 Newton on object 1. We have a drag force of 100 Newton and 100 Newton on object number 2 also. So what is the equation for drag? Give you by half rho u square CD times A. So same with the B. So the first component is the same. Half rho u square is the same because the magnitude of u is the same, rho is the same. So what you can play with the equation is only you can play with either you change the CDA or an area of A balance with B and A, right? So you want to have 100 Newton so that your CD must more than B. This component must more than B. This is just an experimental determined value. So don't surprise by the size of the object. Don't be surprised by the size of the object. It's just that sometimes it looks small, but the drag coefficient can be big. Okay. Don't confuse with the size. We are looking at shape, not size. Be careful on the confusion between shape and size. This is size. In this case, size doesn't matter. All right. So it's the shape that matter. Okay. Shape. First on the left, this shape will if you have a CD 1.2. Then it will be logic to have the CD 0.12 for B, provided that we have an assumption that both generate same amount of drag. Okay, so this is how we explain the phenomena by equation. Yes.
Also, in practice, size doesn't matter. It's only the shape.
Yes. Size, yes, but size is a bit more general term. If you use shape, shape means what seen by the object, what seen by the upstream velocity. Means you fly from front. What did the object will hit the area? Okay. So this is just an illustration why sometimes a small object can have a very high CD compared to a big object or different size, but you have a low CD value, low drag coefficient value. Okay.
So in other words, it may be like the area of impact by the drag.
Area and also the shape. You see this one, this one you only have circle. So, but this one you have the streamlining. So if you imagine at the flow, so a flow will come here, go up, and then go back here. You know that just now we see one example. We have a separation point. So separation point will generate turbulence at this region. So turbulence will create more drag on the object. So rather than this object, if you imagine you are the flow particles or air particles, you go up and then follow the streamlined body. So it will, if you compare both, then your CD will change. So this is the more on the shape, more on the shape, right? Yeah, more on the shape. Yeah. If you try to, this is maybe a bit extreme to compare both. So what happens if I give you a same diameter of ball like this one? For example, I give you same 10D here, for example, but the shape is round. One is the airfoil shape. So CD for round will be 1.2, a bit higher than the airfoil shape. The argument point is the shape. Okay. All right. Now then the another one, this one you can read. So you can see the amount of wake. This is wake. WAKE wake. WAKE wake. Okay. Wake region. Okay, then this one is for question 26, the answer for question 26. Main category of Reynolds number, of course, depends on the Reynolds number dependence. So we know that Reynolds number, we have a few category. So in this case, we have very low, medium, and very high. Okay. So we have a very low Reynolds number, moderate Reynolds number, very large Reynolds number. And why there's no number given here, because it's just a general statement. Because if you use different medium or if you use water, it will give you a different Reynolds number. If you use air, it will give you different Reynolds number. At different temperature, different Reynolds number also. So we can only view it in a very general dimension. So if you want to study drag coefficient, one of the area that can affect your drag is that the Reynolds number in three types. So either you can have very low Reynolds number, moderate Reynolds number region, or very high Reynolds number region. So we know that above moderate Reynolds number, you will have turbulent layer. Okay. So yeah, here it just gives you some guidelines. So low Reynolds number refer to Reynolds number less than 1. Reynolds number less than 1. Okay. So again, Reynolds number less than 1, we categorize as a low Reynolds number in a textbook. And if you have a very low Reynolds number category, analyze for drag coefficient, it is only the balance between two factors. One is the viscous effect, one is the pressure force. Right? If the question asks you to analyze in the very low Reynolds number flow, to find the drag coefficient is only affected by two factors. One is viscous, one is pressure force. Okay, and you can ignore the initial effect. All right, and CD, this is just the illustration of equation that we can develop later on. So this is just an illustration how we modify the equation for the drag coefficient. All right, so we change according to a constant value. So this one also a diagram under question 25. This diagram is, yes, any question? Any question? No, okay, I'll continue. So this diagram gives you a low Reynolds number drag coefficient given you by this one, the Reynolds number equation again. So if you look on the, you have 4 objects here, 1, 2, 3, 4. So one is slice a cylinder perpendicular to the upstream. One is cylinder object slice, and the flow is parallel to the surface, top and bottom. And the Reynolds number given here, this one. Okay, Reynolds number, this is a cylindrical flow given you by this equation, 20.4 Reynolds divided by Reynolds number for this setting, 13.6 divided by Reynolds number if you have this setting. If you want to calculate the CD, you want to calculate the CD. This is a CD value, CD value, the drag coefficient for low Reynolds number. And this one on the right hand side, you will see C and D. This one is a 3-dimensional object, sphere and hemisphere, which is half, mean the object will hit the flat surface before it continue to the round surface at the back. So you will see the drag coefficient also a little bit different, 24 and 22.2. Okay, per Reynolds number. So in final exam, normally this diagram will be given, and you need to cleverly choose the correct drag coefficient accordingly. So for example, you calculate the Reynolds number. All right. So again, just a reminder for your final exam, most of the time you need to start with the Reynolds number calculation. Calculate the Reynolds number first, then you start look at the scenario that you need to use. Right? You calculate the Reynolds number by the calculation by the equation given. If the Reynolds number less than 1, straight away you refer to this table, and you refer to the individual setting. If you're given a sphere, then straight away use CD equal to 24 divided by Reynolds number. Okay, Reynolds number you calculated already, right? So you straight away can find your CD value, and then go ahead and calculate the drag. Drag equal to drag, okay, drag given by half rho V square A and your CD. So this equation you must memorize. We'll repeat many times throughout this module. So this one you can see the ratio between these two. There is some ratio there. So another one graph is that this one is on the CD, again general one with the Reynolds number. So on the bottom here is if you increase the speed. Again, Reynolds number can define by a few parameters. Usually, commonly, we refer to the velocity. So sometimes it can change to your rho. It can change your diameter. It can change by the viscosity also. It will affect. These are the 4 parameters that can affect your Reynolds number. But in general, for the simplicity, we always use velocity to illustrate the statement. Okay, so if you increase the velocity, you will see what happened to the drag coefficient. So if you increase the velocity, the drag coefficient will drop. One line is for smooth sphere. One line is for the smooth cylinder. So again, there are many graphs that will be given during your final exam. Be careful to choose the correct line when it comes to your exam or your assignment or other question that you come across. Or if you have a different viscosity, if you change the viscosity, it will affect the CD also. If you change the density, it will change it will affect the CD also. It will change the diameter of the sphere. It will also change the CD also. Okay. All right, so this one you read yourself. Another one is on the separation. What I mean by separation? If you don't have if you have an ideal case, then you don't have separation. Separation means you don't have the wake region, or you don't have the turbulent region. So if you have a separation, then you'll see something like this. If you draw the streamline across the round body. And if you have a further scenario, usually it's a process from A, B to C. If you have an ideal case, mean at a certain velocity, you will have an ideal case where you don't have a separation. Then by some setting, for example, you change the velocity, you change the Reynolds number, then you will have some separation bubble happen. And then if you further increase the velocity, then you have turbulent after the object. So this phenomena is called oscillating Karma vortex street wake. So of course, this is a very bombastic word. It just illustrate that turbulence is happen after the body, after the certain point of the body. But this phenomena by mathematician and also by scientists. They have named this phenomena as oscillating Karman vortex strict wake region. Then there's a difference between laminar body layer, we have a wake, and also narrow turbulent wake. So you have white, means the distance is very big, this is white, and you have a very narrow wake. Okay.
So the wakes all, it depends on the velocity, so what?
It depends on the shape, it depends on the velocity, like the drag coefficient just now, there are like 6 factors that can affect the creation of the wake. But these are the phenomena that we can observe from experiment or from the normal daily life phenomena. So sometimes why do you see there's a vacuum, or sometimes why you see a big turbulent wake or narrow big turbulent. These are the common observation that we will have. But of course, it won't happen in one scenario lah. It will happen either mixture 1 or 2. Okay.
Okay.
Right. So yeah, this is the experiment on the round cylinder body. So this one later you open the PowerPoint slide and you can go and look in the YouTube lah. Okay, it's just a flow visualization experiment for this one, and this one is the flow around the cylinder body, how they conduct experiment to get the this observation. Okay. Another one is the diagram with a different shape of object. So again, Reynolds number here changed a little bit, not changing, but you are using different viscosity. Just now it's dynamic, but if you change to kinematic, then your Reynolds number equation change to this form. And your CD on the left. So what happens if you have a flat plate? What happens if you have airfoil? What happens if you have ellipse, circle, and flat plate? So this diagram will help you to solve some problems to estimate the CD that you have. For example, from the calculation of the Reynolds number, you use this graph, project up. Let's say you find that 1/10⁵ for flat plate, then you project to the left, then you get one number. Right? Same with this one. If you have one Reynolds number in the middle, you project up. Let's say you have an ellipse body, you project to the left, you get one of the CD value. Then you can calculate your drag force on the ellipse body for this example, and drag force for the flat plate from this example. Okay, this is just to expose to you that we have all these different kinds of graph to help you to get the value of CD. All these are gathered through experimental data, and this one are all generalized. Means there's a handbook that give you the more exact value of all these. All these are published in a journals paper. Okay. Let me see the time. Oh, it's almost time. Yeah, let's look at one question, and then maybe we can call it a day. All right. Let's look at question. Yeah, any question? Any question?
So I think that does temperature affect the viscosity force, viscosity of the fluid?
Which one? This one. Again, your repeat your question.
I think like on Reynolds number, it's divided by viscosity, the denominator, right?
Yeah, you mean this one, right?
Yeah.
Yeah. So this one, if you still have the, let me see, if you still have the exam paper, if you still have the exam paper, or you have a textbook that I show you, you look at table 1.6. Okay, table 1.6, or maybe I show you. Okay, So you are confused with the Reynolds number. So okay, so open up the, if you have this textbook, so this one. Okay. So if we have table 1.8, your Reynolds number given by different viscosity, it is this one. It can either give you in dynamic viscosity, or you can define as kinematic viscosity. These two. All right. So if you look at under Moody chart, most of the time you use this one. The diagram that I give you, they use kinematic viscosity. It is this one. Okay. Yeah.
So it means it's that Reynolds number we know as the rho.
You mean
Usually we are using a rho VD over.
Yeah, correct. Because the kinematic viscosity equal to rho something. Yeah. There's a conversion from this one to this one. Kinematic and dynamic. There's a equation to convert this one to this one, or this one to this one. Yeah. So kinematic usually is you have a movement, a very fast movement, then you'll use kinematic viscosity. But anyway, all this value can refer to the respective table. For example, in this case, you refer to 1.8 to find your Reynolds number according to the different medium here. Okay. Yeah. If you mention about density, yes, density is affected by the kinematic viscosity. So there's a specific section discuss about the kinematic viscosity in Reynolds number. So if you're interested, you can go and look into Reynolds number definition and what is kinematic viscosity, what is dynamic viscosity. Okay. All right. So let's look at this diagram, this tutorial question. I want you to change something on the question, which is the unit, this one. All right. I think this one I find the answer in unit SI, so I forget to change the imperial unit. So this one I think is 8 meter. Let me check. The solution I think is in 8 meter. Yeah, no. Oh, this is just to illustrate the conversion. All right, we fit with 8 feet in this example. Okay, normally in exam you won't see imperial unit lah. This tutorial purposely put fit there just to show you there's a conversion from imperial unit or English unit into unit SI. Okay, now this question asks you the application. It's an application of low Reynolds number flow drag scenario. So this scenario is where workers spray a paint, and we focus on the paint particles. So numerous small paint aerosol dispense into the air. Eventually, this particle will settle and fall to the floor or stick to the surface. Consider small spherical paint particle given by this diameter, or 10 micron. A specific gravity Sg given by 1.2, mu water given by so and so. You have specific of the water, you have air and raw air. Okay. So how do we solve this question? So you draw a free body diagram of the particles, and this one again, this example is for low Reynolds number flow drag. So when I mention low Reynolds number, you should recall one table that particular focus on low Reynolds number, right? Just now, there are 4 particular diagram that give you a low Reynolds number table, right? Okay. So in this particle, you draw one particular Reynolds particles, one particle in round shape. Because the statement, the question statement tells us that this is a round body, spherical plane. So we draw a round circle, and then we put in the drag the force component on the free body diagram. So we start with the velocity from the bottom, because the particle drop, right? The particle drop from the air into a floor. So the velocity will pick up from the bottom. The arrow will point up, right? The arrow will point up to represent the upstream velocity. And we assume that the body is stationary, right? Oh yeah, although we know that the particle is dropping, but again, there's a relative perspective that we can assume that the particles is stationary while the flow is flowing from bottom. Okay, yeah. So on the object itself, we have a 3 component force. One is the weight of the gravitational effect, which is give you the weight, the mass times the gravitational give you weight, and then there's a drag force, which is always opposite of your motion, and then you have a buoyant force here, means a force that pulling the particles, that make the particle float a little bit. All right, so you have 3 forces in a free body diagram and 1 upstream velocity. So in exam, if you draw this one, there's some marks there, as you can see in your test one. So if you draw something, you'll have some marks for the diagram. All right. So from free body diagram, just balance the force. So to balance the force, W equal to D plus the buoyant force. So of course, you can develop from axis, so Y, all the force up there is positive. So you can write all the force in Y equals 0. This one you learned in your static already, right? So W is going down, negative, plus D plus FP equals 0. So from this one, you get this equation. Right. Then to find the volume of the particle, how you find? You take the specific weight times the volume, you get volume. You get the weight of the specific weight times volume, you get weight. Yeah. Because if you refer table 1.8 again, do we have specific weight here? So specific weight you have here. So gamma, specific weight in the unit of Newton over meter cube. So if you take volume, if you take specific weight times volume, you actually take Newton over meter cube times meter cube, you will get Newton at it. Okay, so if you take this one, you will get weight lah. Okay, weight in Newton. So this is how you do dimensionless analysis. All right. Now, how you find how you convert the specific weight of the pane, because we don't have specific of the pane in the table 1.8, because in your exam usually you only have table 1.8. There's no pane here, but you have air, you have water sometimes. Okay, but here you don't have water, but it's given in the question statement. So what you convert is that you take the specific gravity times the water, then you can get the specific weight of the pane, and the volume of the sphere given by pi divided by 6d cube. Okay, this is mathematics. Okay. Then the FB, the buoyancy force. Buoyancy force is given by specific weight of air times volume. Right, volume of the sphere. Also, volume of the sphere given by pi divided by 6 d power 3. So you have W, you have FB. Okay, we have solved for how to find the weight for the pane. In this case, there's a reason why the question gives you specific gravity SG and the specific gravity for specific weight for water and air, and the pane is not given. You need to know how to convert it. In this case, it's pane, so it might change to a certain scenario where I give you a chemical. Okay, I give you a chemical, like your test one. I give you a chemical, then you change. Then you solve the question. Okay, in this case, we have our weight component, we have FB component. Then the drag. How you find the drag? Again, you pull out the drag equation. D equal to half rho V square CD times A or ACD. All right, it depends on how you memorize. So you just substitute. Rho in this case you use air. U in this V in this case you substitute with the U square. A in this case is pi r square. All right. So again, be careful when you use the drag equation. The area in the equation always what is seen by the upstream. Always you refer to upstream. What do it see from this perspective? So when the upstream velocity hit the ball, it will see there's a cylindrical area coming in front of the upstream. So how do you get A is a pi r square or pi d square divided by 4 in this equation? So in this slide, you can already balance everything. Can balance everything in this equation. W equal to D plus FB equation. And in this case, we assume, although the statement do not, the question do not say that this is a low Reynolds number, but we know that this fall under this chapter. So if you refer to the table just now, in this shape, table under question 26. So just now you have this table. I open up the slide. This one. Okay. So just now you know that we are looking at very low number, and we have a sphere object. So straight away we can use CD equal to 24.0 divided by Reynolds number. So continue with the calculation. You replace your CD with 24 divided by Reynolds number. And Reynolds number, how you calculate, also given in the table just now. Rho UD divided by mu, and this one is the dynamic viscosity, right? If you take out the rho, you convert rho divided by mu, then you get kinematic viscosity. All right. Now from here you can make comparison already. Just now you, one of you asked. Reynolds number, you have two equations. Rho UD divided by mu, or just now in one of the diagram you see something like that. So you can see from this equation, kinematic equation equal to rho divided by mu. Okay, this is kinematic viscosity. This is dynamic viscosity when you do conversion. So to answer the question just now, actually the effect of density is still there. It's only mathematic. It changed some form only. Okay, I hope these notes here will explain the question just now. Right, the rest is just mathematics. You summarize the equation, you will get 3 pi mu a ud. This one you calculate the Reynolds number will be 0.00251. Okay, once you get the Reynolds number, of course, from the Reynolds number, it just to confirm, double confirm that this is a rho Reynolds number, because we already define what mean by rho Reynolds number. As long as your Reynolds number less than 1, you can use the table that I showed you just now. All right, the table for rho Reynolds number drag coefficient. All right, that one, the table is under question 26 in your hands-on. Okay. Back to the question just now, you combine, you're able to find the u inside the question, because just now in this equation d, we have arranged at, we arrive at d equal to 3 pi mu a ud, right? And all the parameter we need for w, that one, this one we already defined. So all the form that we have here we already can find, only the u that we don't have inside the drag coefficient, drag equation. So you substitute all the value, at the end you get your u equal to point something, right? 0.003 something, right? Again, this is just an example, right? Try to understand what you're trying to do, right? We find the equation for w, we find the equation for drag, we find the equation for FB, we rearrange the equation, refer to the correct table. At the end, there is still one unknown that we do not know, which is the u. U is missing in the equation, so you find the u. So from the u, you can find, right, the time to reach the floor. So we know that speed is distance divided by time. So rearrange, get the time equal to distance divided by speed. Just as a side note, there's a conversion from feet. So the question purposely give you in feet, because just to illustrate that sometime in the real life you need to involve with the conversion of unit. So in this case is 8 feet convert to 2.44 meter. Okay, so this is just a highlight. This is just a highlight. In normal exam paper, you won't see the mixture of English unit or imperial unit. All you will see is in a unit SI. Okay. So at the end, you can find the time equal to 600 something second, 668 second. All right. Yeah. So this is just to illustrate the strategy we use to solve the question that involving drag equation, weight equation, and then recall back what you learned for the specific gravity, what is the specific weight for water, and so on, how it linked to our question. Okay, so what happened if I change this question to chemical atom, right? that you shoot across to eject this molecule into high speed. So what happened? How you, all right? How you, in this case, it dropped. So what happened if I shoot a molecule, a round molecule, or a gold molecule, right? A gold atom which is in circle. So I shoot this atom from a horizontal position. So what is the free body diagram that you should draw? So all these are the strategy we test your understanding in applying the knowledge that we cover in lecture. Okay. So I think we already cover for question 27. All right, then if you print out the, okay, I think I will stop here. Okay, I will stop here. Yeah, I will stop here. Then we continue next week for under compressibility effect. Or you can still continue. Then we can, let me see. I think there are a few more slides. There might be cover next week. Okay, we stop at question 27. I'll stop the recording.